Question 8. A scientist is studying the growth of two different populations of bacteria. The number of bacteria, n, in the first population is modelled by the equation n is equal to ae to the kt, t greater than or equal to 0, where a and k are positive constants and t is the time in hours from the start of the study. Given that there were 1,000 bacteria in this population at the start of the study, and it took exactly 5 hours from the start of the study for the population to double, part A, find a complete equation for the model. So we're starting with this equation here. N is equal to ae to the kt. And initially, we're told that there are 1,000 bacteria at the start of the study. So this means n is 1,000 when t is 0. So let's put these numbers into our equation. So 1,000 is equal to ae to the power 0. Since e to the power 0 is 1, we have 1,000 is equal to a, or nicer, a is equal to 1,000. The next thing we're given is that it takes 5 hours for the population to double. So when t is equal to 5, n will be equal to 2,000. And substituting these values in gives us 2,000 is equal to 1,000 e to the power 5k. Now we want to find k, so let's divide both sides by 1,000. And so 2 is equal to e to the power 5k. And now taking the natural log of both sides, then the ln 2 is equal to 5k. Dividing by 5, then k is equal to 1/5 of ln 2. Now I have a value for k, and I have a value for a. I can write my equation for n. N is equal to 1,000 e to the power 1/5 ln 2 times t. Part B. Hence find the rate of increase in the number of bacteria in this population exactly 8 hours from the start of the study. Give your answer to two significant figures. Well, we're starting with our equation n is equal to 1,000 e to the power 5th ln 2 times t. Now, when we see the word rate, we're looking at the change in the number of bacteria over time. This would be dn by dt. So we need to differentiate this equation with respect to t. So differentiating with respect to t, when differentiating e, it remains the same, but we multiply by the derivative of this component. So we need to multiply by 1/5 ln 2. Simplifying that gives us 200 ln 2 e to the 5th ln 2 times t. We want the rate 8 hours after the start of the study, and so we want when t is equal to 8. Substituting 8 into our expression, we've got our dn by dt is equal to 200 ln 2 e to the 5th ln 2 times 8, which is 420.24 and so on, which gives us an answer of 420 to the two significant figures asked for. The number of bacteria m in the second population is modelled by the equation m is equal to 500 e to the power 1.4 kt, where k has the value found in part A, so that's our 5th ln 2, and t is the time in hours from the start of the study. Given that capital T hours after the start of the study, the number of bacteria in the two different populations was the same, find the value of t. We're told m is equal to n when our time is this capital T. So we can write our equation for m with the capital T is equal to our equation for n with the capital T. Dividing through by 500 gives us the following. Taking the natural logs of both sides here, on the left, taking the natural log of e to the power, these will cancel and leave me with the power, but on the right hand side, if I take ln of 2 multiplied by e to the 5th ln 2t, it's the same as ln 2 plus ln e to the 5th ln 2t. And so where we've got the ln next to the exponential, they will cancel, and so I'm left here with the power 1.4 lots of a 5th ln 2t, which is equal to ln 2, And again here, the ln and exponential cancel to leave me with the power of 5th ln 2t. If I subtract now 1/5 ln 2t from both sides, I'm left with 0.4 lots of a 5th ln 2t is equal to ln 2. And so to find a value for t, I need to divide ln 2 by this 0.4 lots of a 5th ln 2. And evaluating this on our calculator, we get an exact value of 12.5, which is our number of hours.